So I'm going to repeat this question a number of times throughout the semester. What does it mean to say that we know the distribution of a random variable x, um, but by which I mean probability distribution or theoretical distribution, something that um, is a provides deductive um, tools for inferring probabilities associated with different values of x. It means that we know all the values that x can take on, and we know the probability of x falling in any reasonable set we can name. And we can, well, I'll leave this as a review question for you, different ways that we can characterize these probability distributions, specifically theoretical rather than empirical ones. We've talked about this before. In principle, we want to know all the features of a distribution, and if we know the distribution, we have those at our fingertips. We're able to answer any of those probability questions. But there are some important summaries, typically, especially if it's a well-behaved probability distribution, if it's not too jagged or weirdly shaped. And one of the key things we'd like to know is the mean of the distribution, the expected value. And this is not exactly the same as the empirical mean or the sample mean, as you might call it, the average. But they're connected, and the most typical way of estimating the mean of a true distribution or a theoretical distribution is by using a sample mean. And that's because we have certain long-run guarantees that as your sample gets bigger, you have a sample mean that's going to get arbitrarily close to the expected value of the distribution. That's something that Bernoulli, who is mentioned in your book club reading, proved with his law of large numbers. So how do they differ? Well, you know already, to get a sample mean, a mean of an empirical distribution, it involves, let's just for formality's sake, write out if your random variable is, we'll stick with x here, if x is your random variable, and if xi is the ith observation, so maybe these are heights of people, and so xi is the height of the ith person in your data set, or the ith row, then the sample mean, that is the mean of the empirical distribution of your actual data, is found by adding up all of the individual xi's from I equals 1 to whatever your sample size is, and we'll call it n. Sorry, that's I equals 1 to n, right? And dividing it by n, right? So this is, you kind of do instinctively now. Add together the values and divide by the total number, right? So that's the sample mean, and it's one approximation of the true mean, or the theoretical mean. So if we want to know the expected value of x, which we can write as mu or mu sub x, right? These are two ways of writing the same thing. We might estimate it with a sample mean. And we know that the sample mean for large sample sizes can get arbitrarily close. That is to say that we can guarantee for any small difference between that we might like between x bar and mu x, there's some sample size large enough that we can get those two arbitrarily close within that size that's specified. Okay, so that's what we were talking about. An average or sample mean is not the same as an expected value, and to clarify that, we'll take a look at a distribution and think about how you would calculate an expected value from a theoretical distribution, not from before even seeing any data points. But first, we need to just review or introduce what a random variable is in order to talk about what it means to calculate things like expected values and variances. And so, loosely speaking, a random variable is assigning numbers, assigning values really to any event that we're interested in a so-called experiment. It doesn't have to be a true experiment, it could be observations. And typically mathematical probability thinks of these as assigning numbers. So even though in principle, we might think of, like, let's say something like wealth, we could categorize it. It could be categorical ordinal like this. You could have negative, you could owe money, you could have exactly zero, you could low, medium, or high. That's something that's based on actually a continuous random variable, but simplified into ordinal categories. If that's the case, if that's the grouping that we do, then sample space might be the set of all households from which we're selecting one of these categories. And so we might assign numbers to it. But, to think even outside of a variable that's a number to begin with and is just simplified into ordinal categories, we could think of going back to the colors example, 7 different colors that a car company makes its cars in. The random variable of color observed on individual cars or purchases is going to manifest as an individual color, and we can give those numbers for the sake of computation, but the numbers don't have any inherent meaning. And so typically we assign numbers, and if they're categorical variables, then we'd assign arbitrary numbers. So to keeping it to that definition, knowing the distribution of random variable is knowing all the values x might possibly assume, and knowing the probability of observation falling in any subset. This is easier in some ways when we're working with a discrete random variable. In other ways, it's harder. And so in the case of a discrete random variable, x is that it can take on either finitely many possible values or infinitely many but countable. I can put them into one-to-one correspondence with the positive integers, right? So example of that I've mentioned before might be that there's no theoretical maximum to, let's say, the number of let's say one's counting individual bacteria in some piece of bread. There's no automatic maximum to it, so we might have that count be any number from 0, 1, 2, 3 toward infinity. Even though infinity, it's not going to be infinite, but we don't want to put a fixed bound on it. So that's still discrete. We're still counting them, as opposed to something like on an interval, like height or weight or income, which is continuous. So the distribution function is collecting information about probabilities of various subsets of interest, or how to actually calculate those. And so for us, often that means a function in R. And we've seen ways of characterizing probabilities in terms of distribution functions that start with P for probability that x is less than or equal to any specific number. And those are cumulative distribution functions. And in the case of a discrete random variable, we also have probability mass functions that look like probability that x equals any given number. We've done that with binomial random variable. We can do that with Poisson. We can do that with a number of other kinds of discrete random variables. So again, cumulative distribution function is literally, it is giving you probabilities. It is, if you give it a particular x, it's going to shoot out, it's going to give you back the probability that the random variable x is less than or equal to that specific number, right? So one thing that must be true of any CDF is that its values are always going to be trapped between 1 and 0, right? So if we've got x, we might have a cumulative distribution function that looks like this. It shouldn't have overlapped there. Like, it could be exactly on 0 from negative infinity up to a certain point, right? So for each value of x right here, the probability that x is less than or equal than that specific value of x is 0, and then at a certain point it starts accumulating probability, over here, the probability that x is less than or equal to this, let's say x star, yeah, it's a bad star, is maybe it's about 0.5, and it's maybe up here it's getting close to 1. It might never get all the way to 1. It might hit 1 and then stay there, but it's going to not decrease as you go left to right, right? So once you know probability that x is less than or equal to some number, if you choose some number bigger than that, the probability that x is less than or equal to that number has to be either larger or the same, right? So you could have a CDF that maybe stayed flat for a bit. It might even jump over here where it accumulates a bunch of probability. It's like if the probability that x equals, let's say, b, has some positive value, then the probability that x is less than or equal to b versus the probability that it's less than or equal to a little bit more, there's going to be a sudden jump in it, in that CDF. But key thing here is the function value, big F, probability x is less than or equal to little x, is always trapped between 0 and 1 for any x. But one thing we can do with discrete random variables that we can't do with continuous random variables is that we can sensibly ask questions about probability that x equals some specific number, right? We know with continuous, it's just going to give you 0. It's not going to be useful. What must be true of, just slapping a mosquito. What must be true of any probability mass function? Well, it's one thing that has to be true is that any specific number that comes out has to be between 0 and 1, and when you sum up all of the values, all of the probabilities for any x's that have positive probability, they have to sum up to 1. Right? Did I write it? I don't think I wrote it, but right, the sum of all of the values of little f of x, all of those probabilities x equals different numbers, equals 1 if we add up all of the f of x's for all of the x's where the probability that x equals little x is, keep it simple, is greater than 0. Right? Add all the probabilities and you get something equal to 1. We'll make it concrete in a second with an example. But a discrete uniform distribution just has a number of possible values. The probability is greater than 0, and the probabilities of x equaling each of those, say a roll of 1, a roll of 2, a roll of 3, a roll of 4, it's going to be equal for all of them. In this case, it's 1/6. That's 1 divided by the total number of values, right? So here you can see that when you sum up 1/6 plus 1/6 all the way up, all those 6 times, you're going to get the 1. So the sum, as we discussed, has to be equal to 1. And each of the individual probabilities is between 0 and 1. So if x can take on k, some number of equally likely values, the PMF is going to look like what? 1 over k, right? It's just different notation. Sometimes they use little f, just regular generic function notation. Sometimes they point out it's the probability function associated with the random variable. Here it's y for any specific little y, and that just means the probability that y is equal to whatever specific little y you give it. Sometimes for shortcut it's just written as p little y. And here are the two things that must be true, just said more formally. The probability that y equals little y has to be somewhere between 0 and 1 for any specific y. It's probably 0 for almost all y's in the interval, because these are just discrete many. And summing them up gives you 1, right? You can't get over 1 as total probability. So here's an example where it's not uniform. Little p of y, the probability that y equals y, when y is -10, it's giving you, that is to say, it's giving you here the probability that y equals -10, and it's saying actually putting almost all the probability on that. It's 999 1,000ths, right? 0.999 or 99.9%. right? So the probability that y equals negative 10, it's almost guaranteed, but there's some small chance, 5 in 10,000, that, is that right? 10, 100, 1,000, yeah, 5 in 10,000, that that y is going to be 100. Probability that y is 100 is 0.0005. Probability that y is 500 is 0.0004. Probability that y is 5,000 is 0.0001. How do you know that this is in fact a probability distribution? Well, all of these are between 0 and 1, right? So for any other y besides negative 10, 100, 500, 5,000, the probability is 0. So if you want to include, we're just adding a bunch of zeros. What's the probability? What's the probability that it's either negative 10, 100, 500, 5,000? It's the sum of all of these, and you can do the summation and see that it adds up to 1. So in fact, it is a distribution. It's a discrete distribution. And this is give us an opportunity to talk about expected value. This is the promised theoretical mean expected value, and to demonstrate that we can calculate expected value of a random variable without any data, just using the information that we have about the distribution, this hypothetical distribution. And this example I'll use is thinking of this as being a lottery, and these being the probabilities of different payouts, like you pay $10 and almost certainly lose the $10, but there's some chance you get your original 10 plus $100 back, so you have some 5 in 10,000 or 1 in 2,000 chance of winning $100. You have a 4 in 10,000 chance of winning $500, and you have a 1 in 10,000. Sorry, that was 4 in 10,000. Yeah, 1 in 10,000 chance of winning a grand prize of $5,000. So the expected value of y, that is your kind of in a frequentist perspective, this is the long run average of if you play it over and over and over again. You can also think of this as a sort of a kind of central tendency of the overall distribution. It is going to be found by taking each of the non-zero values, or each of the y's that have non-zero probability, and basically doing a weighted average, taking each value of y and multiplying it by its probability, right? Sum of y times probability that y equals that little y, summing them together, right? So take each of these probabilities, or each of the values of y that has non-zero probability, and multiplying it by its associated probability and adding them together. You'd probably do this intuitively. Expected value of y is negative 10 times 0.999 plus 100 times 0.0005, so on, right? And what we get out is negative $9.99 plus 0.5 plus, oh, I guess I did this in, interesting. Oh, yeah, no, this is, oh, yeah, this makes sense. Sorry, it's been a while since I did this example. So multiplying these all out, right, each of these outcomes times the probability of getting that outcome, adding them together, we get negative $9.24. So what does that mean? It means that our expected winnings is actually losing $9.24. Again, from a frequentist point of view, it means if we played this game over and over again, we would, on average, lose $9.24. Yeah. All right. There's some other senses in which we can interpret expected value of y in terms of beliefs about what's going to happen, or actually in this case, we could think about it as what is a fair bet, right? So if this was the game, right? If I'm on average losing $9.24, it's not fair to me. I'm taking some small chance at a really big bet, but on average, I'm losing. Let's skip this for now. I want to draw attention. Well, okay, a couple things. Expected value of a constant is just a constant. There's no randomness involved. Expected value of a constant times a function of a random variable is the constant comes out times the expected value of that function evaluated at the random variable. And I should mention this as well. I skipped over it, but the expected value of a function of y, So let's say you have some y with a known distribution, and you're taking y squared. It says that basically you take each value of that function of y, right? So you put in y, each of y's possible values and square it if that were the function, and take that weighed by the probability of y um, being equal to the specific value of y. So aside from expected value, variance is the probably next most important characteristic of a distribution. We sometimes write it as sigma squared, and square root of it is the standard deviation, right? The square root of the variance of random variable y is sigma. Sometimes we're specific about sigma of what? Sigma of y. So sometimes you'll see it with a subscript letting you know what random variable it is taking the variance or standard deviation of. It's defined as the expected squared difference between the random variable and its mean. This mu here is just expected value of y itself. You can do a little bit of algebra, and this would be a nice little practice problem for you if you like math, to FOIL this out, right? Distribute and see why it reduces to the expected value of y squared minus the square of the expected value of y. Right? That second part that's being subtracted there is the expected value of y, the mean of y itself taken to the power 2. And we should talk on Piazza if it's not clear to you why these don't equal 0, why the expected value of y squared is not the same as the square of the expected value of y. I know when I first encountered this, I found it confusing. Yeah, so think about it, and think about it in terms of the definition of expected values, and we can take this up on Piazza if you have a question about why those two things need not be equal and typically aren't equal. So, we have a number of famous distributions that all actually are related to starting with dichotomous 0-1 random variables. The simplest one, actually the ones that we'll encounter, we've already talked about Bernoulli and binomial. Binomial, it starts with a Bernoulli where you're either having a success or failure, coded as 0 or 1, and then binomial says, okay, we're going to take n independent Bernoulli trials, or in R they refer to it as size. They use n for how many times we actually repeat the overall experiment. So we're going to say, I'm going to do something, I'm going to do independent attempts at some outcome, all with the same probability, p, and I'm going to count up how many successes, how many times the identified event occurs. And a Poisson, which is number of occurrences in a fixed continuous time. Things like, where it doesn't have to be time, it could even be space, number of deer in a square mile, it could be number of typos per page, number of deaths per battle, number of criminal sentences of longer than a year for a particular crime, and so on. Yeah. And then so there's some other ones that we're not going to focus on. And so we can talk about Bernoulli distribution in sort of overly formal notation, right? So if P is the probability of success, flipping ahead, or having an outcome that's desired or not desired, you can still call it a success. Probability of failure is 1 minus that p, so the probability that y equals 0 is 1 minus p, probability of y equaling 1 is p, and for any other value of 1, 0, right, it can only be 0 or 1. Sometimes that's called, as I said, little p of y, probability that y equals little y. And the binomial occurrence. There's always some assumptions hidden, and we should make them transparent. So the situations in which you would assume a binomial distribution, or you might use it as a model, it's essentially a model, is that there's going to be some fixed number, known number of identical attempts or trials, right? How many flips of the coin, how many attempts at shooting a basket, how many individual occurrences of the thing under study are we going to see. Each trial is going to have one of two outcomes. Whatever those outcomes are, we can call them technically a success or failure. And the probability on any one single attempt or trial is equal to some value p, and that's the same from trial to trial. So if whether you have a success affects whether you have a success in the next attempt, this is not a good model. That is to say, they're independent trials. The outcome on one does not give you information about the outcome on any other, aside from what it might tell you about an unknown p. And so the random variable of interest is just measuring the number of successes over the course of those n trials. This can be written, the probability mass function can be written as p taken to, right, so the probability of y successes is that probability to the power of the number of successes times q, which is really 1 minus p. It's not a separate number, it's already determined by p, taken to the number of failures, right? It's all these multiplications, because and probability of success and success and success, y of them, times probability of failure and failure and failure, and minus y of them. And this thing here, n choose y, which is n factorial over n minus y factorial times y factorial. Don't worry about it so much. If in R, it's going to do it for us automatically. But basically, it's worth knowing that what that's doing is it's the combinations. It's how many different ways you can have y successes and n minus y failures, because order doesn't matter. So there's the probability mass function. And let's just do a quick examination. Suppose you hit a basketball free throw 60% of the time, and assume that you're not a streaky basketball shooter, so getting a success doesn't make you more likely to get a success on the next ones, and you're not, you don't go cold if you miss one. It doesn't make you more likely to miss the next one. So you make 5 attempts. What's the probability you hit exactly 4? We can do this with D binom in R, which we've talked about already, but we can also do this with a formula. 5 choose 4, which, again, I'm not going to ask you to do this, but for those that are find the arithmetic fun, this is going to be 5 factorial over 4 factorial times 1 factorial, which the 4 factorial cancels out top and bottom, and it's just equal to 5. There's 5 different ways, and where's this 5 come from? This constant 5 is that really that you can. I'm not going to write it out, but you can, if you're shooting 5 and you hit exactly 4, you can hit the first 4, you can miss the second one, you can miss the let's see, you can miss the first one, hit the others, you can miss the second one, hit the others, miss the third one, hit the others, miss the fourth one, hit the others, miss the fifth one, hit the others. So there's 5 different ways that you can hit 4 and miss 1. And it works out to a probability of just under 26%. You make 10 attempts. What's the probability you make more than 2? We can do that. I'm going to leave that for you to do in R if you would like. I will point out that if you're doing it by hand, it's a lot easier to figure out the probability that you make 1 or 0 and subtract that from 1. Right? So you can try that using this. You can find it. You can do it by putting in a 0, and you could put in a 1. You could add those together and subtract from 1. Whether it's appropriate for this situation depends on whether you think that your shots are independent or not. And I've been going on for an awfully long time, so I think I'm going to stop here. I just want to note that whenever we have a named distribution like a binomial, one of the virtues of that, of making the assumptions that go with that model, is that we know everything there is to know about the distribution by just using math that's been understood for a long time. And so the average of a random binomial variable y is equal to the number of attempts times the probability of success, right? So if my probability of shooting any basket is 60%, if I tend to 60% of the time make my baskets, then if I shoot 10, as you might expect, 10 times 0.6, I can expect to hit 6 of them. I expect to hit 6 of them doesn't mean that I'll be surprised if I don't. It means it's a long run average. And then the variance is n times probability of hitting any one of them times probability of missing any one of them, and the square root of that is the standard deviation. So in the case I just gave, this is a question here. On average, I expect 6. My standard deviation is square root of variance square root of 10 times 0.6 times 0.4 is 2.4. So again, even though I expect, quote unquote, to hit 6, right, typically from one group of 10 shots to the next, there's going to be a bit of diversity. I'm very loosely speaking, going to typically be off from the average by 2.4. All right, that's it for now.